Hello, this is a short lecture on chemical kinetics. So without further ado, let's get started. Now, what's kinetics? Chemical kinetics refers to how quickly the reaction proceeds, rate of reaction, Pseudo of the reaction. So let's start out with the collision theory of reactions. Chemical reactions occur when reagents collide with each other. Molecules, the atoms, the molecules, the atoms, the ionic formulae, and they need to collide at the right angle to form an activated complex. What things affect at the rate at which the reaction proceeds? What affects how fast the reaction goes? Let's talk about some things just to get them over with: temperature and catalysts. All chemical reactions to get started require an activation energy. Simple example is striking a match. The friction between the match and the surface when you strike it creates enough energy to get the match burning. A catalyst lowers that activation energy. The lower activation energy means it can proceed more quickly. Temperature, that increases the energy of the reactants. What is temperature? Temperature is an indirect measure of the kinetic energy of atoms and molecules. That's what temperature actually is. Now, we're not really going to talk about this in this lecture. We're going to talk about something else, how it affects the rate of reaction. Concentration, pressure, and volume to surface area ratio. More collisions, and hence more reactions, will take place if the reagents are more tightly packed together. All these things we're going to think of as concentration, how tightly packed they are together. And we're going to be using this symbol. I'm using capital M because the units we're going to be using is molar. Which we all know, the units of 1 molar is 1 mole per liter. So we're going to think of everything as concentration, but in gases that is pressure, how much is packed together, and in solids that's surface area to the volume ratio, as shown as this diagram. More surface area to volume, more ways the solid can react. But we're going to think of everything as concentration for the sake of this lecture. Now look at this. Rate of reaction is a function of concentration. The rate of reaction speeds the reaction, reactant disappears, and a product forms. Look at the diagram. Product goes up, reactant goes down. Let's look at this. As the concentration of the product increases, what's happening? The slope, that is the rate of that reaction, the slope of this tangent line is the rate of that reaction. It is the derivative, okay? So in this case, the rate of reaction is going to be d A over dt, where A if you know your calculus, this is just called the derivative. It's the slope of a line at a single point, as opposed to the slope of a line determined by 2 points. Slope of a line tangent to a curve touching at 1 point. That is the instantaneous rate of change at that point. It is like speed. It's just like linear speed, which we talked about in physics. What are the MKS units for rate of reaction? So that's going to be molar, okay? Since we're using molar for concentration, you can say this is not really MKS, but it's still, since molars aren't strictly MKS units, they use liters, since molar per second, okay? This is kind of bad notation. It should be just M per second. But those bars mean concentration. Rate law. The rate law will tell you how the reaction proceeds based on the concentration of the reagents. The rate constant, this is your rate of change of the reaction, the SADU, slope of the curve, okay? And the equation to the left, A, B, and C are the concentrations, and X, Y, or Z are what's called the orders, okay, of those reactions, okay? This is an exponent. You will see in some textbooks that this exponent is the stoichiometric coefficients of the reagents. So let's say we have 2H2 plus O2 yields 2H2O. You will have some textbooks that will tell you that the order of this reaction, of these reagents, is 2 for hydrogen, 1 for oxygen. It might be, but no, you can't tell it from just that. And what we talked about earlier, about the activated complex, is the reason why. You can't just say from the concentration of the reagents and the order of this in the stoichiometric coefficients, that's the order. It's one of the things that's involved, but it's not the only thing, okay? Order of a reagent. The order of a reagent shows how the concentration of the reagent affects the rate of reaction. Now, sometimes you'll see some playing fast and loose with terminology. We have order of reaction here and order of a reagent. The total order of reaction is something else. It's the sum of the orders of all the reagents. But of all the things being equal, if we have a reaction where reagent A is of order 0, this is what its concentration as a function of time is going to look like when the reaction is proceeding, and the rate will be constant as a function of concentration. If the order is 1, this goes down, okay? This is going down like this, quadratically. And the rate as a function of concentration is linear. A2, this is also going down nonlinear, and rate as a function of concentration is quadratic, since it's order 2. Total order of reaction. The total order of a reaction is found by summing the individual orders of each reactant in the rate law. For example, if the reactant is first order reaction, if a reaction is first order in reactant A and second order in reactant B, the overall order of the reaction is 3. Now, what are the MKS units for the rate constant K? Now, that's going to depend on the total order of reaction. For here, we know that the rate is molar per second. Okay? If the reaction is order 0, anything to the 0 power is 1, so K is just this. Okay? So K, for a 0th order reaction, K is in molar per second. For a first order reaction, okay, we raise a concentration to a first power, okay? So we have molar per second is K times molar, which are the units for concentration. Molars goes away here, and we have K as reciprocal seconds. For a first order reaction, K is the same units of Hertz as Hertz. Okay? Now, for this second order reaction, we have the power of the concentration is raised to 2. So we have rate here, molar per second, K times molar squared. And now K, the units for K, notice we can cancel out 1 molar from each side. And the units of K here are going to be 1 over molar seconds. We find these orders using something called the initial rate method. Look what they're doing here. They have a series of fixed times. It could be this many seconds, okay? What they're doing is actually they're measuring the average rate of formation of a product through different times, okay? With the same initial concentration of the reagents. They do that several times and then plot a graph and try to calculate the initial rate of reaction, okay? Now, we repeat this experiment several times. And again, we actually do in the lab, we have to actually do it several times with the same initial concentration over different times, okay? And then just change the initial concentrations of the reagents, do the same thing, and see what we get for the rates of reaction. Now, let's solve problems using the initial rate method. Let's say we've done 3 overall experiments and calculated 3 initial rates for this reaction. Ammonium and nitric ions in solutions yields nitrogen gas and water. Well, the reagent we're probably going to be collecting is the nitrogen gas to find the volume, okay? Well, let's answer this question. What's the rate law? The rate law, R, rate for rate, is going to be K times the ammonium times the nitric, will be called the ammonium X, we'll call the nitric Y, nitric order Y. Now, what's the order of the ammonium? How are we going to figure out from this data? Let's look at this. Look at experiments 3 and 2. Notice that the nitric concentration is the same, okay? But the ammonium concentration is doubled. And look at this, the rate of reaction is doubled. So we have R3 over R2 equals K we had 0.2 here, 0.2 times 0.01 all over K (0.1) y here. Y and this equals 5.4 over 2.7, which is going to be 2. Now let's look what happens. 0.1y and 0.1y go away, okay? And these k's go away. We are left with 0.1, 0.2 to the x over 0.1 to the x, and that's going to be 0.2 over 0.1, which is 2 to the x, equal 2. So x equals 1. First order in ammonium, in the nitric oxide. Now let's look what we have here. This is also, look at experiments 2 and 1. R2 over R1 is also 2. 2.7 is twice as big as 1.35. And again, this is divided, we have half the concentration of nitric oxide, while keeping the ammonium the same. And the K's cancel out, and we will also have Y equal 1. So it is first order in both of those ions, the ammonium and the nitric. And the rate constant K, again, we can just say, we can use any one of these. Well, let's use experiment 2. 0.1, so we have R is K. These are both 1 now, so we have R, which is going to be 2.7 times 10 to the negative 7 negative 7, and that's going to be K times 0.1 times 0.01, and that's going to be, we take this, we multiplying by 0.001, that's going to be the concentration of those, and since they're both order 1, and now we divide this K is now .7. We're dividing by 0.001, that's multiplying by 1,000. times 10 to the negative 4. And since this is an overall order 2 reaction, its units are 1 over mole seconds. 1 over mole, not moles, molar seconds. Okay. Thank you very much. That is an introduction to rate orders and rate constants. Next time, we were going to talk about the integrated rate law and maybe discuss equilibrium. Thank you very much. I hope that was something you were looking for. Thank you.